everyone. Welcome back to SAT Math Question of the Day with Professor Emeritus Seth Chaiken, University of Albany, and Seth's brother Joel. You are here to hopefully help you approach SAT math questions. Here is a question 20. We're getting toward the end of the questions in this section, and this is a calculator section. Well, frankly, it doesn't look like the calculator is going to be necessary just by glancing at this thing. Okay.
No.
So everyone, look at it, pause the video, and come back. The mass of living organisms in a lake is defined to be the biomass of the lake. If the biomass in the lake doubles every year, which of the following graphs could be the model of the biomass in the lake as a function of time? Doubling every year. So this question, hopefully you can do in about, 3 seconds? Hopefully.
3 seconds, yeah.
3 seconds, right? Right, because you got to do these questions. Yeah, right. So it's the only one that would be considered exponential growth is, Seth said this one.
Yeah. Well, you need to recognize that doubling every year is exponential growth. Exponential growth is growth, and it's nonlinear. And also, biomass does not increase in discrete steps, sudden steps. So certainly not this. It's not this because this is linear. The biomass as a function of time equals 1 times t.
Right.
Here, biomass as a function of time equals 1 times 2 to the t. Well, let's extend.
A half. Technically,
really?
A half.
No.
A half.
When t equals, yeah, you're right. Yeah. Good. Excellent correction. Yeah, the constant is a half. Times 2 to the t. And let's check it. When t equals 0, well, it's a half. When t equals 0, we have about a half. When t equals 1, we get 1/2 of 2 to the 1, which is 1/2 of 2, which is 1. When t equals 2, it doubles from 1 to 2. Okay?
Right.
So far, it's the same, pretty much the same as this. But take one more step. 3. It doubles from 2 to 4.
Well, they don't show that.
They don't show it. That's right. They don't show it. That's your problem. But that's his 3. Here's 4. Here's the point. 3, 4. And then it's even worse when you get to the year after the 3rd year, 4th year, we get double of 4, which is 8. It's all the way up here. So if you drew you extend the curve, and it looks like this.
Right. So it's 2 to a power. It's 2 to a power.
It's 2 to the power. Yeah.
It's 2 to the first.
Well, no, it's not 2 to a power. It is 2 raised to the power that is the time.
Yeah, that's right. Yeah.
So the power is variable.
Right. No. The base is 2. The base is 2. The
right.
power is the x. The power is the independent
but 2
variable.
is the base, and x is the exponent.
Right. Yeah. That's right. Yeah, that's what that is. Yeah.
Right.
Yeah. And this is a kind you forgot to say.
But I think in this case, when you review linear versus exponential growth, recognize that doubling is a case of exponential growth. Multiply for each step in time. Multiplying by a constant is, the constant is greater than 1, it's exponential growth. And then recognizing the difference in the shapes of the curves between linear growth and exponential growth.
You said multiplying by a constant is exponential growth?
Well, you multiply by a constant for each constant increase in the in the independent variable in the time. Each time you take a step in time, the value grows by a constant factor.
Right, constant factor. Right,
Yeah,
right,
that
right.
constant factor is the base.
Right, the base of the exponent.
Right.
Yeah.
And the exponent is the this in this problem is the amount of time.
That's right. Yeah, exactly,
Right.
exactly.
Yeah.
Now, many
Okay.
people, well, hopefully, people will be watching this 100 years from now. Who knows whether they'll even have the SAT? Who knows if they'll have, well, they'll have the internet probably. Who knows what's going to happen 100 years from now? But in the short term, in the people watching it in the 2023, 24, 25 timeframe, everybody probably remembers COVID and what happened in March 2020 when COVID came in the world. And people will, if you go back to the graphs, remember the graphs went like this. For the beginning of COVID, the growth was exponential. So we've all lived through exponential growth. Living through an exponential growth thing is usually not the greatest. Usually bad stuff. But good things can grow exponentially. But most of the time, it's not very great stuff. And that's it. So that they really live through an experience of exponential growth.
Well, there's a remarkable long period of exponential growth in computing technology. That's called Moore's law. It's been growing according to Moore's law for how many decades? It's like 30, 40 years. That is the growth of, like the power of a computer, how much computing it could do for a fixed price. Has been growing exponentially as time goes by, and it's like I don't know, it doubles every year and a half or so.
Right.
Although there are indications that, and there are theoretical reasons for us to expect it to slow down a bit pretty soon.
The other thing that actually is, it's exponential growth. This is a good thing. Investing money. If you invest money at let's say 4% a year, it grows exponentially. It's a very slow exponential growth, but it is an exponential growth, and that's an example of a good thing that grows exponentially. So I guess that's it, right?
That's it.
That's it. Wasn't there a question a few days ago about exponential growth where we had to divide the time by 1690? There was a doubling. There was a half-life. Was that? No. That wasn't here. Was that here? I forgot.
I think we had one a few days ago.
Yeah, I think we had one a few days ago.
Yeah.
Okay, right. So it's really important on the SAT to recognize linear growth, exponential growth, and it doesn't hurt also to recognize quadratics, like a quadratic equation.
Quadratic growth
equal to x squared. Do they have quadratic growth? Is that a word? Quadratic growth?
Sure.
Okay, yeah. So quadratic growth is y equals x squared, which is a parabola. Which, if we make little spelling, we'll just do it here. Parabola. So that's the normal parabola. Parabolic. Do they say quadratic growth or parabolic growth?
Well, I think they can say either way.
Yeah. Okay. So that's the one that that's the one. Oh, what is going on? Are you kidding me? That's the one that goes like that. It looks a little bit like exponential, doesn't it?
Well, it's concave upward. And increasing slope, the positive second derivative. So in terms of that shape, they're the same. But quadratic growth is the case of two of power law growth.
Right.
Where 2 is the power.
Right.
So as a where t is time, the amount is proportional to t raised to a constant power.
Right.
So for quadratic growth, the constant power is 2. Well, you might have a power like 2.5, or 3
Yeah.
or 10.
Right.
Well, the feature of exponential growth is that, well, what determines the amount of exponential growth is the base.
Right.
Right? And if you take any base that's greater than 1, even a little bit greater than 1, and you take any power like 2, 3, 4, 5.5, 10, 1,000, and you compare the power growth to the exponential growth, there'll always be some time, possibly in the very distant future, when the quantity that growed exponentially exceeds the quantity that grows by a power growth law.
Right. That's right.
No matter what the power is, as long as it really is growth, that is positive, and as long as the base of the exponential is more than 1. And that's something that's a topic that you would look forward to learning about in calculus.
Right. So wait. So we're really getting ahead of ourselves. We should say goodbye to everyone. Yes. We should say goodbye to everyone.
Goodbye to everybody. Yeah, I think I'm done on this
Yeah,
rant.
yeah. I think we're done on this.
Yeah.
Okay. So then today's Friday, so have a great weekend, everyone. And we'll see you next week. Okay. And like us, dislike us, give us comments. Please, we need the comments to know how to change this to do better for you. And please email us your SAT math questions at satmathquestionoftheday@gmail.com. Bye-bye, everyone.